Hello and welcome with the new video. So this is conformation of propane today. So let's make a propane molecule first. I'm Professor Dr. Mchem from Dr. Mchem's Institute of Chemistry, University of St. John's. I'm here to make a propane molecule. So we have 3 carbon atoms here. Okay, so now I'll start joining them. CH3, CH2, and of course then again CH3. This is the magic of the 3D drawings or 3D models, that you can simply see the connectivities, how the atoms are connected together, and I mean you can simply see the angles they are forming and the positions they are getting or attaining. That is, I mean, the different dihedral angles forming between them. So this is something amazing. So I'm going to make you see the propane molecule. Okay, so this is it. Just visualize this. So this is simply you can call it a perspective drawing or perspective model, 3D model of propane, right? CH3 and CH2, and of course again CH3, right? So now this is how you can visualize it. I mean the bonds that are projecting towards the viewer and the bonds that are away from the viewer that are going into the page. They are represented by the dashed lines. These are by the solid wedges, and some of them are in the plane of the pages. These are again projecting. This is again a solid wedged in the 3D structure. This is the dashed bond, and this is again this one again is the dashed bond, right? That is projecting away from the viewer. So this is simply a perspective 3D model. And now if you see it through a Newman projection, how you're going to visualize by a Newman projection. So let's do that. For that, well, for that you need to make it look like something like this, the Newman projection. This is it. Yes, the carbon with the 3 methyl groups, right? And of course the back carbons that are there behind, and then the methyl group that is attached down here. So this is how it can be viewed when you will look at through a Newman projection formula. This is the Newman projection formula, right? This is how you can visualize it when you are actually looking at a Newman projection. This is a Newman projection. Newman projection, right? Formula or a Newman projection drawing, right? So now here the propane, as you know, it's a 3 carbon alkane. It has 3 carbons in it. It has the formula C3H8, right? It has the formula C3H8. Yes. Now here simply you can see a 3D structure, a Newman projection of this compound called propane, and it is simply when you are looking down one of the carbon to carbon to carbon bonds, right? So how it would be like that when if the viewer is somewhere, you can see like this. If a viewer is looking from here, right, this is an eye, a viewer is looking towards the compound called propane, what it would be like, carbon with a dash bond, solid wedge, and of course again attached to another carbon that has got a hydrogen, and again a hydrogen that is in the plane of the page, and a solid wedge, and then this carbon with a solid wedge, a hydrogen, and of course a hydrogen. So I think I got it. This is how it would be like when it is being, a viewer is looking through, this structure. He's going to observe it like this, right? And this will be equal to what? This structure would be equal to, when it will be equal to the Newman projection. It will be equal to that, the Newman projection, that is this one. Finally, he's going to see this structure that is called a Newman projection, right? In which you can only see the back carbon, and the front carbon and the back carbons, and of course the methyl group, right? So this is when it's simply looking down one of the carbon to carbon bonds. This is how it will looks like, right? I put a blue paper down so that you can easily see the Newman projection, which I just prepared it for you people of this propane molecule, right? How beautiful it looks. When the viewer looks from here, he is going to observe through the carbon to carbon axis, right? And then he is going to observe, if he observes it as to a Newman projection, it would be like this. If we talk about, or if we discuss the torsional energy of propane, especially via carbon to carbon bond, when it rotates, the torsional energy, it will again vary, just like it does in ethane. We have discussed ethane previously, so the rotation would be just the same as was in ethane, but of course there's a difference of energy that is now here. How much energy would be needed? 13.8 kilojoule per mole of the energy would be required, or 3.3 kilocalories per mole would be required. If we draw the potential energy diagram versus dihedral angle, which I will just make it now in front of you so that you can see. So 13.8 kilojoule mole, or which we call it 3.3 kilocalorie per mole. So only you can say that 1.2 kilojoule, that is 0.3, which is equals to 0.3 kilocalories greater than the required for ethane would be used now. So the torsional strain would result from eclipsing the carbon hydrogen bond. When what is happening, when the carbon hydrogen bonds are eclipsing, you will of course observe a torsional strain around within a carbon methyl bond, which is only 1.2 kilojoules that is 0.3 kilocalories more than the, which is greater than the strain of the two carbon hydrogen bonds when they eclipse. So I just show you now how it goes on. Make the figure, a rough figure, which I have just made it for this is simply potential energy, right? And this is the dihedral angle theta, which is equals to here 0, then of course 60, then of course 120 degrees. You will observe in the graph, this is of course the graph of propane's torsional energy, and what would happen as one of the carbon-carbon bond, it will rotate. So of course the torsional energy regarding the eclipse conformation is almost about 13.8 kilojoules, which would be like this, right? It would be like this, and then again it will go up, and then again it will decline. It will be like that, right? It will go up, because this energy is 13.8 kilojoule per mole. So now apparently it's simply the torsional energy of this eclipsed conformation is almost 13.8 kilojoule per mole only, and it is 1.2 kilojoule or 0.3 kilocalorie greater than that was required for ethane. So I will draw the formations now, that you can see different, the eclipsed formations. It would be like this and this, and of course it would be like this. This is eclipsing, CH3, right? This is H. This is again eclipsing, and here again see another H. So simply the angle between now this angle would be, of course, 0 degrees, right? It's in the eclipsed formation, so this would be 0 degrees, right? Whereas this corresponds, this figure, this eclipsed conformation, it corresponds to this one, right? Whereas at 60 degrees, when at carbon bond it rotates to 60 degrees, what happens? CH3. So what you're going to see, you're going to simply see the angle when it rotates. This rotation is 60 degrees, right? 60 degrees rotation between hydrogen and methyl group, right? The angle between them is 60 degrees. So you can see a decline, right? At this staggered position, right? Whereas again, when it again goes to the eclipse formation, what you're going to observe, just make it again here, this corresponds to this one. Now for this, CH3. So now hydrogen, 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 hydrogen. Okay. So now here simply you will see that the bond between this and this is 120, and this methyl, right, it's 120 degrees. So here again simply you will see that how much, of course, this corresponds to this 120 degrees. So now this is 13.8. So this is what is happening here, that about 13.8 kilojoule mole, which I just explained earlier also, kilocalorie per mole, or you can say 1.2 kilojoule, 1.2 kilojoule, which equals to 0.3 kilocalorie more than that required or needed for ethane. Ethane would be needed. So of course the torsional strain resulting from eclipsing, when you eclipse a carbon hydrogen bond with a carbon methyl bond, that is carbon methyl bond, is only 1.2, that is this much, 1.2 kilojoule, which equals 2.3 kilocalorie more than the strain that was when the carbon hydrogen bonds they eclipsed, right? So this was the main difference between the other one and now. I hope you followed this easily, because now this was simply the torsional, I discussed the torsional energy of propane. When you simply see the carbon-carbon bond of the propane, when it rotates, it goes the rotation, the torsional energy, it changes, it varies, it intensifies, just in the same way like an ethane, but with, of course, with a difference of 13.8 kilojoule per mole or 3.3 kilocalorie per mole of the which energy, the torsional energy, in which conformation? Of course, in the eclipsed conformation, this one and this one, eclipsed conformation, eclipsed conformation, because the eclipsed conformation is facing the torsional strain, which I've discussed in the ethane in very much detail. So I hope you understood today's lecture, today's simple conformation of propane molecule, its structure and how it looks like, the staggered, its Newman projection formula, how it it's shown here, which I've explained, and what happens when it simply you plot a graph between potential energy and between a dihedral ligand, with the theta is increasing from 0 to 120 degrees, and what are the changes when the molecule, the rotation occurs between the carbon and carbon to hydrogen bonds and carbon to methyl bonds. So this was something very interesting. I hope you like it. You will learn it more properly by looking and comparing your results in the book. So that's all for today. Thank you very much.